using truth tables, also to apply statements using logic concepts. Am I audible enough?
Yes.
Okay. As for our introduction, we'll look at the rules of logic. Of logic they give precise meaning to mathematical statements, and these rules are used to distinguish between valid and invalid mathematical arguments. Besides the importance of logic in understanding mathematical reasoning, logic has numerous applications to computer science as well as to our everyday life. In logic, a statement is a declarative sentence that can be either true or false. Logic is the discipline that deals with methods of reasoning, of which we say logic provides rules and techniques for determining whether a given argument is valid or not. Logical reasoning is used in mathematics to prove theorems, in computer science to verify corrections of programs. That's why we use logic. And in our daily lives, logic, we use it to solve a multitude of problems. Then we have statements in logic. A statement or proposition is a declarative sentence that is either true or false, but not both. So take note on that one. It's either it's true or it's false. We can never have two situations whereby it's true and false at the same time. When dealing with logic statement, the truth values of true and false are usually denoted by the capital letters T and F. When we will be doing our truth tables, there we'll see that. In logic, a statement is true. That means its truth value is what? True. A statement is false. This means the truth value is false. For example, rain falls from the sky. Zimbabwe is in Europe. So, like these statements, it's at the end of the day, you must get an answer whether is it true or false. Like rain falls from the sky, is it true or false? Zimbabwe is in Europe. Is it true or false? What are you doing? A simple statement.
Before you go any further, on that one it's not a statement. What are you doing? Can you have the truth value of what are you doing?
So that one goes to the last option that I gave. We cannot have both true and false used at the same time. That one is not a statement. It's very true, say.
It's not a statement. It's
yes.
A statement. It must have a value either true or false. So that one, it's a sentence. It's not a statement. What are you doing? You cannot actually have the truth value of that as true or false. So it's just a sentence. It's not a. It's not a statement. So it wasn't supposed to be there. It wasn't supposed to be there as an example of a statement there.
Okay, sir. Thank you, sir, for that one. Thank you for that correction, sir.
Yes, sir.
Hello.
Hello. Yeah, I wanted to add, like, I think that example was to show that rains fall from the sky. That is true. That's a true statement. That's true one. And then Zimbabwe is in Europe. That's false. And then what are you doing? It was supposed to show that a statement is not true and is not false, which means it's just a question. It's not a statement.
Yes.
But the way you put it doesn't mean it. If you give it to someone and someone is reading that, I think that person will not get that information.
Yeah, I think there was a mistake. There's an error there.
So that's why I'm saying so, because these slides, some of the people will be actually reading them.
Okay, sir.
Yeah.
Okay. Can I continue?
Yes, you can.
A simple statement is statement that cannot be broken down into smaller terms. In this case, a simple statement is denoted by a lowercase letters. For example, we have P, Q, R, and S. Examples for Q, there we say the sky is blue. In this case, Q is a simple statement. Then for S, we say humans breathe underwater. Then we move on to compound statements. Where you don't understand, good people, may you interject me so that we make clarifications with other group members who are here present, where you don't understand. A compound statement is a combination of simple statements and logical operations, of which these logical operations we have earned.
I can't hear anything from this side here.
And not.
I think there's network problem.
In this case, a compound statement is normally denoted by the use of the lowercase variables P, Q, and R. Examples. I finish writing my computer program before lunch. Then Q, I shall play tennis in the afternoon. R, the sun is shining. S, the humidity is low. So combined, take note, like in the first when I explained the compound statement, I talked of logical operations. So now we're joining these statements. So if joined, it will read as if I finish writing my. So take note of the if that I've used at the beginning of my statement there. If I finish writing my computer program before lunch, then I shall play tennis this afternoon. The operations that I've used there, it's if and then. The sun is shining and humidity is low. Take note, the operation that has been used there is and. Then we move on. Like let's, as an example, we created a table with the proposition on the left side, then what is not a proposition on the right side. We have 4 plus 9 is equals to 18. On that one, you can get an answer whether it's true or false.
Okay.
There are
May you return to the back slide?
The previous slide.
Yes.
All right.
I wanted to understand on the use of these variables which you were talking about, P, Q, and R. Me, I'm not understanding where they are being used at.
The variables P.
Yeah, Kuti, in what sense exactly are we putting P in the P is representing what in those variables? I hope you are getting me. Hello.
Hello. Yeah, like if you read the second statement, it says a common statement is normally denoted by the use of okay. Those are just but variables that are used for those compound statements where we have
Alright.
P, Q, R, and S.
Hello.
I'm having
Yes.
Maybe I can add.
My network.
Maybe I can add on that one.
Mhm.
You said a compound statement is a combination of simple statements.
Yes.
So let's say we are having two statements that we want to join to become one.
Yes.
The first statement will be represented by P. The
Yes.
second statement will be represented by Q.
Yes.
Or if there is the third statement, it will be represented by R.
Yes.
Okay, now I now
Thank you.
understand. I now understand.
Thank you for that clarity. Thank you for that clarity.
Also,
Okay.
guys, take note of this. These are just names or variables that we can give to any statement, so that you can write it. So that you can write it maybe in shorthand. Otherwise,
Okay.
P, Q, R, and S are the most commonly used. It's now like the way you do with the for loops. You see that when you put a for someone is going to put an I, someone's going to put an J. You are not going to see an A there, but if you put an A, it's not, there is no an error that you are going to encounter. So that's what it is like here. P, Q, R, and S, these are just common variables that we use to represent our statements so that we can write it as a compound statement.
Thank you very much, sir, for your contribution.
Okay.
Thank you.
Thank you very much, sir, for your contribution, and thank you very much
So it's
also
just
for the questions you're asking. They are making a lot of sense.
ABCD.
Hello, Divine. Your network is poor. Maybe it's better you use the chat, or you can just raise your hand there. I will spot you and then I will call up on you. Okay, you can.
Can I continue?
Present. Yes, you can continue.
Okay. Okay. Thank you for your questions, guys. They are really good questions.
Hello?
Yes. So, like I was on this slide, I was saying there are what you call propositions, and there are some that are not propositions. Like firstly, I said 4 plus 9 is equals to 13 can be classified under propositions because we can get a result as in true or false. Then as a second option, there are 365 days in a year. That one, the result also can be true or false. Milk is white, same as above, as well as humans are just fish with legs, which you can come up with a result either true or false. Let's look at the other statements that are not propositions. What is your name? When somebody says, what is your name? You cannot get a result for true or false. And if somebody says, wait for me, we cannot have a result true and false. X is greater than 4 is equals to 1. X minus 8 is negative. I think those examples are very clear. Can I proceed? Okay, yes. We also have what are called connectives. These are the symbols that can be used to join sentences, compound statements. As you can all see in the table there.
You can proceed.
Yes, as you can all see in the table, can you all see the table? There's a connective condition, or the connectives There is follows. We have got conditional connectives, conjunction collectives, negation, biconditional disjunction, showed by the symbols there. As you can see, the symbols and the meaning and what they are called, as shown on the table. Examples. Let's move on to examples. On the examples, I finished writing my computer program. I shall play tennis, as alluded earlier on. I used this example, but this time, if we can look at closely on the slide, I've used the arrow, the arrow from the previous slide. Do you still remember what that arrow denotes? What it says? It's a symbol for what? If and then. That forward arrow. Then we have that sign, we have the not sign there. The not sign Q. I shall not play tennis in the afternoon. So we must get used to these symbols where they are used. Take note, the forward arrow is if then that zigzag like symbol, it's not. Then we have the disjunction, that is all, that V. As you can see on this slide, it's called vel. Yes, I think it's clear. So we have to get used to these signs. Where they are used, you know what's the meaning of the symbol. Sorry. Can I proceed? Right.
You can
now want to translating from English to symbols. Like what was speaking in English, want to translate it in symbols. As you can see, there is the left column is the sentence, and the right column has got the symbolic form. So if we say Mary will not get married, so that not is shown by that symbol, not Q. If Romeo dies, then Mary will get married. This time, check note, I used if then. Check even on the signs. There is a forward what arrow there. Mary will get married and Romeo's family will be happy. We used, on this one, we used and. If Romeo does not die, Mary will not get married, and Romeo's family will be happy. Take note, I used two. I used not and end. All combined. If you check on the table, there's a division there shown by the brackets. Because that one it's a long sentence with the more symbolic forms.
And what are my compound statement that you can?
Yeah.
Also, guys, I think what is also very important here is to get the context. Like we have got variables P, Q, and R. So the first thing is to note what they do mean.
Yes.
Like there we've got a Q.
Yes.
You've got a P, which says Romeo dies. That's the statement there. Romeo dies. And then we've got a Q, which says Mary will get married. And then we've got R, which says Romeo's family will be happy. Those are the initial statements that we have. And then when you change it from Mary will get married, and then you change it to Mary will not get married, it's now the negation of what? Of Q. So you need to get that context. Where are we coming from and where are we going? So you have the statement, Mary will get married, and then we have another statement which you say Mary will not get married, which means if Q was Mary will get married, and then we have the statement which says Mary will not get married. It's now the negation of Q. You are now actually taking the other side of what? Of Q, just like that.
Thank you for that one, Sam. Thank you.
So,
Right.
in other words, it's just the opposite of P.
For the negation, yes, the negation is just the opposite there. Just like what you do in it says, if you've got A and then you want a complement, you know what to do. That's what it is with the negation there.
Okay, thank you for that one. Guys, let the questions come as we proceed, because like it was said earlier on that we need to be moving very fast so that others get time also to present. Okay, we'll move on to the truth tables. The truth value of a compound propositional statement is determined by its truth table. Truth tables define the truth value of a connective for every possible truth value of its terms. It is a complete list of possible permutations of truth and falsity for a set of simple statements. For one to construct a truth table, you have to assign each statement a column, producing an initial list of permutations of truth and false assigned to the sentence letters in the sentence. Determining which columns in the truth table can be filled at a given stage. Determining what truth values to fill into a given column. I think this one, it's if we've used truth tables before, or if we've once come across them, it makes sense. Right, let's look at this one. This one is the negation not, which is denoted by that. Can you all see that symbol? At first, it only means not. If Q is a perfect statement, the negation of Q is basically.
Hello, Atrio.
Yes.
There is a handy by Moses Dimba.
Okay.
Is it a contribution or a question there?
It's a question. What do we mean by permutations? I just need some clarification on that term.
Hello, come again.
Well, I was asking what we mean by the term permutation. May you please clarify what we mean by permutation?
The meaning of the word permutation from the
Yes, sir.
permutation from the previous slide.
Yeah, sure.
All right. Mathematically, we say the action. This is the action of changing the arrangement. The action of changing the arrangement, especially the linear order of a set of items. Is it clear mathematically? The meaning of the word permutation?
Yes.
You can give it an example.
For permutation team, I think these ones you actually focusing on these ones when you are doing discrete mathematics. Yep. But normally we cannot hinder you to learn this now, but when you're doing discrete mathematics, that's where you encounter these permutations. There's a topic called permutations and combinations. The permutations, like now, the way we can arrange things in order. How many times can you arrange this in order? How many times can you arrange these numbers? Maybe it's numbers in some sort of order there. So there's a topic called permutation and combinations. You do that when you're doing discrete mathematics.
Okay, thank you for that one.
So is order important when we are dealing with those permutations of truth? Is the order important?
Like here.
Yeah.
Yes, it's also important. The order is important. Whenever you have whenever you want to find the truthiness of a certain statement, remember for truth table you'll be given a compound statement, and then you break it into simpler statement, each and every statement, and you have the truth value of each and every statement, and then you combine them to have the final truth to the value of that compound statement. So order does matter.
Okay, thank you, sir.
Okay.
I understand now.
Okay, can we proceed?
Yeah, sure.
Okay. Like I was saying earlier, we're now talking about the negation note, which is denoted by that symbol there at first. Then we're saying if Q is a perfect statement, the negation of Q is basically not Q. Then, as you can see on the table, we have got Q and not Q. Can you see that? So if it's Q, that means it's true. Q, that one, true. Not anything that is not Q. So that's what? That's false. So if false, the result on the other side for not, we get what? True, as shown on the table there. Then we move on to and. We will see that the results for not and end, they are different. This time, this is a conjunction and. Take note, we talked of the negation, not firstly. Now we're moving on to the conjunction and. So, as shown on the table, if it's P and Q, the result at the end there, those are the result. We've got 3 columns on that table. So, truth for P and the truth for Q there, then the result is what? Truth. As shown like earlier on, I explained that the true and false is usually shown by capital letter T and what? And F. Where we have 2 options, true and false, then we have a result as false there. Where we have false and truth, the vice versa of the above, still the result is false. If it's false and false, then the result is false again. Yeah, I think these things, so that you're not confused, we need to do much revision and much considerations on these truth tables so that we're not confused.
Also, I think you're supposed to actually put a note there, because whenever you are dealing with a note, there's something that you actually see, actually it happens. Like if something is not true, it's always false. When something is not false, it's always true. If you go for an end, there's something that we have to note there. You're supposed just to document it there. Like if you look on the variable P there, and on the column with the variable Q there, and then you look on the variable, the final one, which says P and Q, you will see that we've got a true ones and then we've got false there. What a conclusion can you draw there? Because those are the nuggets that can actually help you when you got stuck with these logical operators. What a conclusion can we draw there on that column, on the truth values of that P and Q?
Okay, for what we can conclude is that whenever we have got different where we have different options, either it begins with true or ending with false, the result is what, when we're dealing with end, the result is always false. Even if we start with false, or even if we start with the truth, the result at the end will be false. But however, if it's the truth on the other column and the truth on the other column, that's where we have a change.
Exactly. So you were just supposed to say that it is true when and only when both P and Q are true.
Okay, sir.
And it is false if either P or Q is what is false.
Yes.
Or if both are false. So
yes,
those things, I think that can help you. Even you find it on the application. If you do maybe in programming, if you are using this logical and operator, maybe you are saying if A is less than B and B is less than maybe C, you find out that it only execute the following statements if the first one and the second one are both true. So it's just the same as here. It is only true whenever P and Q are what are true. If
Yes,
one of
sir.
those is false, then P and Q is what is also false.
It's false.
Yes, so that one is the conclusion. And we must get it from all other logical operators. We must have that conclusion.
Okay, sir.
Okay.
Thank you, sir.
Okay.
Right. I'll move on to the disjunction or shown with that symbol V. So for this one, or is exactly the opposite of the previous one, the conjunction and. So on this one is when we're dealing with or is exactly the opposite of what? Of and. When we talked of and, it's only false when both P and Q are false. That's where we only get the false result. But for everything, whether P and Q, it's true, there's truth, and there's false on the other side, or even if it's both, it's truth, P is true and Q is true, the result still is the same as true. Even if when the value of P is truth and the value of Q is false, the result again is also true. So take note, for us not to forget this, and or is just or is opposing the result of and. The opposite results of and, we find them on this disjunction or, as is alluded on that statement above, that it tells us that at least on this case, and they are only false when both disjuncts are false. Then we move on to a conditional if then. A conditional statement tells us that if an antecedent is true, the consequent cannot be false. Thus, a conditional statement is only false when a true antecedent implies a false consequent, as shown on the truth table before. When P is true and Q is true, the result is true. But when P is true and Q is false, the result is what? Is false. So take note of this difference now. Whenever, like you see on the second row, we started with the truth for P and the false for Q, then we're only getting the false result there. Then when we begin with, when P is the false and Q is true, the result then becomes what? True. Also, when P is false, also when Q is false, the result again on this one will be true. Take note of that above statement that I read on top there.
Yeah, so it's just like here, Tim, just like when you say if then, you are saying if the first variable is true, then the second variables follow. So it's just this one implies this one, like here, just P implies Q. So whenever something is true, implies something true, it means the final statement is what? Is true.
True.
If something is true, but implies false, it means that that thing is what? Is false. We cannot have something that said to be true and then we see that it's what? It's false. So it means it's what? It's totally false. But if something is said to be false, but implying something true, it means that total thing is what? It's true. It's true. The value is what? It's true. So that's the idea behind that. If something false implies, if something false implies what? Implies false. It means that statement is true. Because false can only implies what? Implies false. And it nema dzinoburitse nema ndo zvazvinokureva handiti. And nema
Yes,
nema
very true, sir.
and nema and
Never
nema
nobody said me.
exactly. This was just
Yes.
so that's the basic idea there.
Maybe I've got a question.
Yes, you can ask.
Maybe just want a clarity. So what you mean is this: if statement says, if Zimbabwe receives adequate rainfall, farmers will not have bumper harvest. It means the statement is false.
Then on that one now it's like when you want to, it's now on the values of P and Q. All right.
Yes, that's what I want to understand. That was if the first statement is true, that if Zimbabwe receives adequate rainfall,
Yes.
then we all know that logically that farmers will harvest will have bumper harvest, isn't it? But if the
Yes.
statement says farmers will not have bumper harvest,
Which means it's now what? The result is what? Its truthness is what? It's false, and it?
I just want to do that clarity if that example fits in.
Yes, it's
Okay.
now false. And even if you put it on the truth table, the first part will be representing P. If we have what adequate rainfall, and it's P, right? And then the Q will be that you have what was the second part? It was you not
Farmers will not have bumper harvest.
okay. So the Q there is we have the bumper harvest, and then that one is now the negation of what? Of Q, which means it's now false. So you'll be having truth.
Logically.
Yes, logically it will be now false. So you have true. True implies what? False, which means you get what? You get false. If you put it on the second row there on PQ there, it will be true implies what? Implies false. And then the result is what? It's false.
Thank you.
I don't know if you get the way that I put it on the truth table there.
Yes.
Yeah.
Okay, can I proceed?
Yes, you can.
Okay. As we move on, we've got what are called what is called biconditional. On biconditional, we're saying we're using if and only if. It tells us that either both are the case or neither is. And a conditional statement is true when both statements are true. Take note of that one. Underline on that one. The statement is only true when both statements are true or when both statements are false. Let's move on to our truth table there.
Atwell, wasn't
Hello,
it
sir?
supposed to be a biconditional statement is true when both statements are true or when both statements are false? It's supposed to be biconditional.
Okay.
So there was an error there. It was supposed to be biconditional. Yeah.
Okay. So, as you can all see,
Maybe did you get what he's trying to say? There is a typical error there.
or a typing error, yes.
Typing error.
Yes, a typing error.
Maybe that's what he's trying to say.
Hello, what was the
Yes,
contribution there?
that's what it's a typing error. Yes.
Oh, where exactly is the typing error? I was just off my headphones.
Right. We said it tells us either both are the case or neither is. And a biconditional is supposed to be a biconditional statement is true when
Okay.
both.
Yes.
That's where the typing error is.
Okay, sorry.
All right. All right. Yes.
Thank you for that one. I think I've corrected. That was a typing error. Right. So if we're listening at the end of that statement, the statement is only true when both statements are true or when both are false. Like, let's look at the table. When both P and Q are true, so the result is what? It's true at the end there, as you can see. But when it's different now, when the statements are different, as you can see, on P we have true and Q we have false. So that means the result is what? Is false. Even
Also-
vice versa. When
Also,
P,
you guys, hello, you guys, there's something you didn't explain to us there. I don't know if all people appreciate how to come up with the truth table. Because we see that on P they've got true, we've got false, false. On Q we've got true, false, true, false. How do we come with all those values? We just have them printed there. But for someone, I don't know if you are fine with that. You guys, do you know how to come up with all those values? It's basic, but maybe with some people who does not appreciate that.
As for me, I don't.
Well, say.
Yes.
Right. I was thinking All right. We just write for P and Q. We have P and Q, isn't it?
Yes.
Right. So what we do is for us to figure out those true and false. We say 2 to the power n, of which we have two values, which is P and Q. These are just two things. So it's 2 to the power 2, which is 4. So the first pattern on P is it true, true, false, false. And then on Q, it's true, false, true, false. So the same applies when we have maybe 4 values like P, Q, R, S. So we just say 2 to the power, the number of these things that we have. So that's how we decide how to put those trues and false.
Exactly. That's what we wanted there, so that we.
Thank you for that contribution.
There's a mic with some background noise. Like I saw my headphones, like any background noise, not a distractor. Okay, I was just saying on that one, it is very important for us to know that, because otherwise, my values are we are going to have some values which are not actually the one that you want, just because you failed to populate your truth table with the truth values of the variables. So what he explains there, that whenever you have your variables, you need just to check how many variables do you have, and then it will be 2 to the power of those number of variables. Like here you've got P and Q, so it's 2 to the power 2, and then you just use the half rule there. For the first one, since we have got what, a 4, so you have what, 4 values that you want to populate for P. So for the first one, you just do the half of that, the total number that you have, which is what, half of 4 is true. So you just put it true, true, false, false. Or you can even start with the false, false, and then true, true, but you have to maintain that now. So if you start with the true, true, you do that even for Q. So it's true, true, then false, false. And then on Q, you do the half of what, of P, which means if it was true, true, then false, false, you are now saying true, false, true, false. You find out that you are going to have maybe three variables, which will be actually having 8 values to populate. So you start by the half, which means you just first put the 4 truths, 4 T's, like true, 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 and then false, 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 false. And then on the next, you do the half of 4. Then it's to be true, true, false, false, true, true, false, false, true, true, false, false, up to the color, up to the row number 8. And then for the last one, the third one, you just do true, false, true, false, true, false. So you have to be used to that pattern, and then you are good to go. You are now using the logical operator, which will be there. Like here, you're using if and only if.
Okay, sir.
Yep.
Okay, thank you for that one, sir.
Okay.
Then we move on.
Yes, Divine Karubi is raising 2 hands.
Okay. I didn't see you. Okay, Divine Tarubinga, do you have any questions there? Divine Tarubinga.
Maybe he's forgetting that his mic is off.
It's okay.
Can we move on?
You can.
Okay. I'll move on to tautology. It is a proposition that is always true, regardless of the truth values of the proposition of the propositional variables it contains. For it, it's always, take note that the statement that it is always true, regardless the truth values. As you can see on the table below there, for P is true, Q is false. The result is true. Even if the P is false and the P is true. Always true. No result here. No, that's the result that we get here. It's always truth. I think this one is clear.
I think we can give an example of a statement.
Hello, come again.
Can you please come again?
Oh, I was just asking if you can give an example.
I thought that was an example. Right? Can you please return to where we were? Please, Atuel.
Okay.
Right. A tautology is just a proposition that is always true. It's called a tautology. Right. A proposition P that is always false is called a contradiction. All right. Before going to contradiction, right? That's, you see, P. Right. There is true and false. Right. So, right, when P is true and P negation, which means it's just the opposite. So there is a false. So which means P negation is true. So true times true is equals to true. Right? And then we go to false. Hello?
Yes.
Right. So, and then we go to F on P. Right? Which means it's the negation of P, which means on true, we have false. The negation of P is false, that one. So it will be false and false. False plus false is true.
Yes.
Yeah, so
Very
that's
true.
tautology.
Yes, like I explained earlier.
Yes.
Yeah, I think if this one is something which is straightforward. Yeah, when you're saying something is tautology, you're just saying that whenever values that you give it, it will be always true. So on that column, P or negation of Q, you have got true, true. So in that column, if you always have those true values as what? As T, it means that compound statement or that statement is what? Is a tautology. Only just that's what you want. Even if it have got eight rows, those rows, each and every row must have a true as T. A truth value is what? As true or as true, just like that. Then we can actually conclude that that statement is what? Is a tautology. It's always true. Whatever you give it, it's always true.
Okay, thank you for that one, sir.
Yep.
Then we move on to contradiction. For contradiction, we're saying it is a proposition that is neither a tautology nor a contradiction, and it is called contingence. It is a statement that is always false. Take note. It is a statement that is always false, regardless of its truth values, truth values. Like, so, also, take note, we're saying on contradiction, it's the opposite again of tautology, as shown on the last statement, that it is a statement that is always false regardless of its truth values. Like if you look at on the table there, on the first column, P, we've got truth, and P, it's false. Check the results. For all, the results are false, just because it's a contradiction.
But also on your first statement, I'm sure You have made wrong claims there. When you say it is a property that is neither a tautology nor a contradiction, and it is called contingence. What do you mean there? The it, which is on that one, is it a pronoun also? What does it is referring to?
It, which one? At the beginning of the sentence.
Yes, at the beginning of the statement, that on that first statement, when you say it is a property that is neither a tautology nor a contradiction, and it is called contingence. Can you explain on that one?
Yeah, I was also confused there.
That one. You have made wrong claims. Something which is neither tautology nor a contradiction is the one that we call contingence. Not contradiction, we can call it contingence. No. So you were supposed to say if you have something which is neither tautology nor a contradiction, we can call it a what? A contingent. So there is a statement that we can call this one, it's a contingent, which means something which is contingent is something which is neither tautology nor a contradiction. So you have to maybe the first the way you begin your sentence there, when you say it, because we have got that title says contradiction. So when you say it is a proposition, you'll be referring to that contradiction at the top.
Okay, sir.
Yeah, so I think we just say we're just supposed to say if the proposition is neither tautology nor a contradiction, it's called what? A contingence.
Okay.
And we're not supposed to find that statement on the slide for contradiction. Maybe we're supposed to find it somewhere when you be giving some remarks on that. Yeah, we've done the contradiction and we've done the tautology. But there are some cases where we're not going to have a tautology and we're not going to have the contradiction. So that thing that we have will be what will be called contingent. Otherwise, it was supposed to have its own slide where you be explaining this one is contingent because if you look on the final column there, we've got the true and false, true and false. We do not have the truth only or the false only. So it's what? It's called the contingent. That's what you have to do there.
Okay, sir.
Yep. You can continue.
Yes. Okay, thank you for that one, sir. Then last but not least, we look at the logical equivalence. When the truth values for two statements are identical, the statements are said to be logically equivalent. That is, both compositions of the same simple statements have the same meaning. Take note, when the truth values for two statements are identical, so we're saying the statements are said to be logically equivalent. As explained earlier, that is, both compositions of the same simple statements have the same, they've got the same meaning. No difference in terms of meaning. Let's look at the table there. Results as shown on the table. And also take note of the last statement there. We used symbols. We used the symbols. If we all still remember the forward arrow for if then the following symbol there for not, and that one for or. So let's get used to these symbols so that at the end of the day we're not confused. I think this was our last slide is group 4, but however the last slide will be showing the the number or the names of all our group members, of which it's not all of us who took part in coming up with the presentation. This is just but our short presentation as Group 4. Allow me to take this time to thank you, to thank all who took part, and not forgetting your time that you took in explaining some of the points that we missed. You tried to explain them fully, and they were understood by almost everyone, of which even us, the group members who are here present, we benefited from your contributions and the questions. We are done.
Okay, thank you for the presentation. Though you have disappointed at the first, I think on those who will be presenting next, let's make sure that we are always ready to share our slides. We are always on time to share our slide. And also, let's make sure that those who are going to present, they must have that stable internet. That's why I gave you a lot of group members. Like if you are 15, I'll be just saying you are not going to skip another presentation just because there's no one to present, because we've got 15 people there. So out of 15, the probability maybe of getting one there, it's actually something that is high. So let's make sure that we work on that for those who will be presenting late. So I don't know if there are questions. They have got Moses there with the hand. Moses, start a hand.
I will say, I just wanted to say that I would have been grateful if we had an example that uses natural language there, because we've been talking about only P and Q, the negation of P, the negation of Q, but we haven't had an example in natural language.
Okay. So do you mean your question is it directed to the truth tables or just basically in general, like the statement using variables and the statement using the English language, the natural language?
That was directed towards that last slide of logical equivalence. As you can see, that table contains several truth values, so it might become confusing when it comes to the natural language.
Okay. I think it's now like the way we form the truth tables, as well as the way it was explained. Maybe you didn't get it. Okay. For that truth table, what is trying to convey is that whenever you are given a certain statement and said to be equivalent to another statement, right? You are just saying if we put those two statements on a truth table, those statements on their truth values must have the same and in the same order their truth values. Like the P implies Q, and the negation of negation. There is a mic which is actually giving us some feedback here. So if there is and then the negation of P or Q there, if you look at those two columns, we have same values. Whenever I've got a true on that column, on the other column we've got what? We've got a true. Whenever I've got a false on the other column, and on the another column we've got what? A false. That's how you can ascertain that these statements are what are logically equivalent. So if you want to put it in an English statement, you are required to find two statements that can you give you what the logical equivalence. Maybe for the sake of an example, if I say 2 plus 2 is equal to 4, it's true, right? And then and then if I say 1 plus 3 is equal to 4, it's true, right?
Yes, it's true, sir.
Yes, those are two different statements, but they are logically what? Equivalent. They are logically what equivalent that we are talking about. We have got the variables P, Q, and the negation of what of P there, with all those variables with the different values there, but you are actually ending up having what? The same output from those two statements. So that's the logical equivalence that we are talking about there.
Thank you, sir. I get it now.
Yep. So for the next group, I don't think I can manage. They can present on next Tuesday, because for today I use public transport, so I think I have to go for now. So I will do post the recorded meeting maybe tomorrow. Now I'm rushing. I'm going home.
Excuse me,